Thank you, Vitaly, for your kind introduction, and my great thanks to Sergey Filippov for the invitation to contribute to this conference. Today, I would like to discuss with you our recent results based on using of block copolymer micelles in the field of oxygen biosensing. Well, and first of all, I would like to discuss with you why we've chosen this field of research, because actually, if we are talking about the importance of oxygen biosensing, it's quite difficult to overestimate significance, because we need the knowledge on the oxygen distribution on all the levels of life organization. And if we talk about for example, intracellular level, we always need to know information about the cell respiration, about the exact concentration of oxygen inside mitochondria or endosomes or lysosomes. And even more important, that we need to have some dynamic information about the changes of oxygen concentration in response to various stimuli, external or some internal processes that happens inside cells. If we go to the intercellular level, again, we also should know here the dependence of oxygenation as a function of the organized cell structure, because even in the case of the rather primitive cell organizations like spheroids, for example, even in this case, we can see the gradient of oxygen from the outside, from the surface to the inside. And going to in vivo gives us several important information. For example, I would highlight the discovery of hypoxia regions in bone marrow. These regions are absolutely normal, and they are related to the stem cell development inside the bone marrow. So the using of oxygen sensing is quite beneficial in terms of deeper understanding of basics of life. And of course, we also can visualize diseases and treat them. And for example, at this right picture, you can see a mouse with a subcutaneous tumor xenograft, which is situated right behind the front paw of this mouse. And if we will visualize oxygen distribution in this case, we will easily find the place of hypoxia strongly associated with tumors. So oxygen biosensing is a very important tool now in nowadays biomedicine. And if we talk about different ways to visualize oxygen, we will find that one of the most convenient ways is to use phosphorescence. By its definition, phosphorescence is type of luminescence that arises from excited triplet states. And due to the triplet nature of these states, we have several benefits of these systems compared to, for example, conventional fluorophores. First of all, the triplet states usually lie lower in energetic diagram, and as a result, we have less energetic photons that usually fall into the so-called window of transparency of biological tissues. This region stems from 650 nanometers and lasts up to 900 nanometers, and most of phosphors, phosphorescent molecules, easily can be tuned to emit in this field. And also, due to prohibited nature of triplet to singlet transitions, we also have long lifetimes in this case. And for example, if we deal with fluorescence, we deal with nanosecond lifetimes, and if we switch to phosphors, we deal with micro and milliseconds. in the excited states. And due to long resistance in these excited states and due to triplet nature of this state, we also, of course, deal with strong quenching by triplet oxygen. And probably this feature is the most important for our research because phosphors, their emission of phosphorus intensity and lifetimes, which is more important, are quite sensitive to the oxygen concentration. Well, and if we deal, and if we will take the lifetime as a parameter to measure, we go to the field of phosphorescence lifetime imaging, or abbreviated as PLIM. And the essence of this method, which is quite useful in oxygen biosensing, the essence of this method is ability to not only create and get some phosphorescent signal at each pixel of the biological sample we investigate, but also to create the decay curve in each pixel. And as a result, after creation of the decay curve in each of the pixels, you can recalculate these decay curves into lifetimes, and you have lifetime mapping of a living organism or of a cell in the case of microscopy. And if we are lucky enough, and if we have phosphors that have linear and straightforward correlation between lifetime and oxygen concentration, in this case, we can also reconstruct the oxygen concentration distribution throughout the biological sample. Sometimes we can only qualitatively assess the distribution of oxygen here. Sometimes the sensors are good enough to make quantitative analysis. Well, but what are the requirements for the ideal PLIM sensor in this case? First of all, it should be mono-exponential. In this case, the interpretation of decay curves and their conversion into lifetimes is straightforward and obvious. Of course, it should have the linear dependence on reciprocal lifetime on oxygen concentration. And of course, this linear dependence should be insensitive to other biasing factors like temperature, pH, presence of biomolecules, viscosity, etc., etc. And if we will look at the modern contemporary sensors that are present in literature and in market too, we will find two, probably the most advanced types of sensors. The first type is just a polymeric nanoparticles prepared from hydrophobic slightly charged polymers with embedded platinum porphyrin complexes inside. They are pretty good and they have rather compact sizes. They have rather good protection of the sensors from the microenvironment. Also, we have here simplicity of preparation because the way of preparation of this nanoparticle just nanoprecipitation, and due to ability to load numerous copies of phosphorus inside this molecule, we have high sense. We can reach high sensor payload if we need this. And of course, due to the cationic nature, these sensors are fastly taken up by the cells. But unfortunately, they are incompatible with in vivo applications, again, due to their cationic nature. Unfortunately, these nanoparticles are large enough to show non-homogeneous intraparticle distribution of sensors, and as a result, we don't have the linear Stern-Volmer plots here. And also, they are not very dispersion stable in aqueous media, especially in the presence of salt due to electrostatic quenching, and they precipitate. And also using of metal porphyrins give us sensors with sub-millisecond lifetimes, which is not always compatible with the experiment, because in this case you need to long dwell times for measuring lifetime, and as a result, your experiment is too long to be performed. Another type of sensors are actually single molecule nanoparticles based on dendrimers with palladium porphyrin cores. After that, we can see the dendrimer, and these particles are coated by polyethylene glycol on the outer as the outer shell. These particles are actually more stable and better protect sensors from the environment due to polyethylene glycol shell, and they provide real linear response to oxygen concentrations, and all the calibration curves that were on the previous slides were from oxyphorus family. And they are applicable in vivo sensing because they have a pegylated shell, but unfortunately their usage is limited to in vivo sensing because they do not internalize into cells. And of course, in this case, we deal with sophisticated synthesis and low sensor payload because these molecules can reach molecular masses up to 70 kilodaltons, and only one sensor copy per 70 kilodaltons is not a very good loading capacity. Well, and if we look at the structures of these two sensors, we of course can easily come up with an idea that it's a good idea to combine both protective strategies. If we will put our sensors into the cores of particles and if we will cover them with the shells, we'll obtain something like core shell nanoparticles with sensors inside. And of course, in this case, we will enjoy by the dual protection from the microenvironment due to the core and due to the shell. And of course, here we also can easily prepare these nanoparticles and get high sensor payload due to the core and ability to place several copies of sensor into this core. And also we will have much more effective dispersion stability due to PEG shell and applicability in vivo sensing. But two questions are still remaining. The first one is regarding the cell uptake and non-homogeneity and linearity of transformer plots. Well, and we managed to make block copolymer Micelles as prototype of these core shell nanoparticles. And also we tried to escape the trouble with too long lifetime in the case of metal porphyrins. So we've taken cyclometallic iridium and platinum complexes instead, because we know that these complexes really have microsecond lifetimes typically. And now we're switching to the design of our experiment. We've purchased several commercial block copolymers. All of them have polyethylene glycol block ranging from 90 to 130 units per block. And also we've managed to take shorter hydrophobic blocks of as different chemical nature as possible. And we've taken lower molecular weight of hydrophobic block to be sure that we will have spherical Micelles, because in our idea, the nanoparticle should be constructed as should have as simple as possible morphology. And spherical morphology seems to be ideal for our purposes. Well, and also we have taken several iridium complexes. Two of them you can see are emittive in near infrared region. Another one emits in yellow region. Also here, I would like to thank our first collaboration by the group of Professor Sergei Pavlovich Tunik from our university, because they have provided several dozens of various complexes, and we could choose from this library the samples that we decided are best for our purposes. And we tried to take as red or near infrared complexes as possible. And also we were searching for as high as possible difference between aerated and degassed lifetimes, because this provides us with the sensitivity of our sensors. And also we've taken several platinum complexes. You can see that their sensitivity is much higher, and their emissions always lie in the field of red region. Well, and these samples were also taken from the group of Professor Tumi. Well, we've used so-called solvent exchange method to prepare micelles. In this method, we start from the common solvent like DMF, for example, and then we add slowly water, and during slow addition of water at vigorous stirring, we obtain micelles, and then we get rid of DMF by dialysis, and finally we get aqueous dispersions of micelles. If we add phosphorus into the starting solution, we get phosphorescent micelles. All the micelles were prepared and were checked for their stability, and we worked only with stable dispersions. And under stability, we understand at least two factors. First of all, they should survive in preparative centrifugation, and also they should be stable for at least 2 months during the storage in a fridge. Well, and first of all, we of course investigated our free micelles, empty micelles, and here I would thank our next collaboration, our second collaboration with group of Professor Tsvetkov, especially I would thank Alexey Lezov and Alexander Gubarev for their dynamic light scattering and analytical centrifugation experiments. And due to their efforts, we found that our micelles are very compact. Their sizes, their radii do not exceed 17 nanometers, but they are not only compact, but rather massive, because their masses can reach up to 2 million daltons, with typically several hundreds of the aggregation numbers. And also we have shown that hydrodynamic invariance of these nanoparticles are resemble those characteristic for spherical and non-percolated and compact nanoparticles. So all the hydrodynamic data tell us that we deal with spherical compact nanoparticles. Then we have investigated the cytotoxicity of empty micelles, and we could show that they are non-toxic, especially those based on caprolactone, which is biodegradable and biocompatible block. And further, we turn to the process of loading of complexes into the micelles, and usually we have observed almost 100% effectiveness of loading into the micelles. So if you take 8% of complex compared to block copolymer, you also get phosphorescent micelle loaded by also 8% of complex. Well, and we also were able to demonstrate that our particles are really spherical. You can see starting particles and loaded particles, and both of them are spherical ones. And after that, we decided to investigate all this stuff, all this library that can be constructed based on our block of polymers and our complexes. You can see that this work is still in progress, because we haven't measured, haven't checked iridium-1 complexes and polyethylene-based block of polymers well, and we have found that some block copolymers didn't work. For example, dimethyl siloxane didn't work, and platinum-3 worked not very well. But most of the phosphorescent micelles were pretty stable, and we then checked them for their photophysical properties, and we were looking for as best as possible mono-exponential decay and as low as possible sensitivity to dispersion media. So we merged lifetime in PBS and then added 10% of serum, and we compared lifetimes in both solutions. And if they were identical, we picked up the systems, and you can see 4 systems that we have chosen. 3 of them are based on polymethyl methacrylate micelles, and 2 of them are based on iridium-3 complex. Unfortunately, the micelles bearing platinum complexes didn't work because they were actually weakly sensitive to oxygen. In this case, we can see that only 15% changes of lifetime upon degassing, and I think it's not enough, not high enough for further development of the systems. And the same situation was for third block copolymer micelle based on PMMA. So it looks like PMMA is too rigid matrix for the complexes, and in this case, oxygen does not reach phosphors and doesn't quench their luminescence. Probably it would be beneficial in other types of sensing, like for example pH sensing or temperature sensing, like this, because in this case you don't have any dependence on the oxygen. Well, but as oxygen sensors, they are not very applicable. Instead, complex phosphorescent micelles based on iridium-3 complex and polycaprolactone were almost ideal because they have shown almost ideal mono-exponential decay, and also they have shown substantial dependence, almost twofold changes of lifetime during the deoxygenation of the surrounding media. And we have chosen this system, optimized it by the composition. We have found that high payloads are not good, and low loading is more beneficial, and we managed to use in further experiment 2 weight percent nanoparticles. And we, of course, taken polymethyl methacrylate as a control in these systems and have performed calibration. We have found that our Stanford plots are almost ideally linear for both systems, but this one is oxygen independent, non-sensitive to the oxygen. And you can see this also in Stanford constants, because for PCl-based system, it's almost 1 order of magnitude higher than that for PMMA-based system. And then we have investigated their cytotoxicity. Unfortunately, PCl-based systems were not ideally non-cytotoxic. They provided some decrease in cell proliferation up to 80%. And now we're trying to understand what's wrong with this system. But nevertheless, the overall cytotoxicity was not very significant, was very high, and we were able to perform phosphorescence lifetime imaging in this case. And you can see on the lifetime distributions that we can have here very transparent difference between normoxia and hypoxia for the case of caprolactone-based micelles. And of course, PMMA-based systems expectedly gave only very little changes in their lifetimes upon degassing. Well, and now we're trying to complete this data, to complete these experiments, and to get more statistics to calculate the resolution in terms of oxygen partial pressure. Can we distinguish, for example, 60 and 40 millimeters of mercury or not? So, but unfortunately now we don't have any statistics for these conclusions, and this work is still in progress. And another direction that emerged unexpectedly was our finding that one of the systems based on platinum-1 complex and the same polycaprolactone copolymer demonstrated unexpected growth of near-infrared phosphorescence upon a successive loading of this system. And we tried to understand what's happening in this system, and we found that neither absorption nor emission spectra do not change in this case, and we assumed that we deal with excimers here, and actually emission decay kinetics performed in the group of Professor Cho at National Taiwan University by our request have shown that here we deal with classical successor and donor type interaction. So this means that our complexes platinum-1 form aggregates inside the Micelles cores, and then the single platinum-1 molecules absorb the light, and then they form excimers, and you can see that excimer emission grows during the time, and excimers do emit the phosphorescence. So in this case, we deal with aggregation-induced phosphorescence ignition, and the mechanism of this ignition is excimer formation. Well, and we also tried to calibrate this system and evaluate as a biosensor for oxygen. We have found that here we deal with much more scattered data, and due to this, of course, they were non-toxic too, and due to this, we were able to only qualitatively estimate the oxygenation of cells. So we can see that in this system, we can easily distinguish between hypoxia and normoxia, but we cannot perform a correct calibration in this case, and unfortunately, we can't get qualitative data from this system. And to go, we go to conclusions, and here I would say that we were able to create stable phosphorescent micelles. They were rather non-toxic. Empty micelles were absolutely non-toxic. Loaded ones were a little bit more toxic, but nevertheless, they all are non-toxic enough to perform some cellular experiments. And we found the best system that demonstrates mono-exponential decays and substantial lifetime sensitivity. Of course, we would like to have higher sensitivity here. We would see not twofold, but 3 to 5-fold difference between oxygenated and degassed lifetimes, but now we have only a twofold difference. And also we found one system that demonstrates aggregation-induced ignition in near-infrared phosphorescence. Well, and of course, thanks to all our collaboration and funding, and great thanks to Anastasia Illistratova, who struggles with these oxygen sensors, and Nina Zharskaya, who developed this AIA project. And thank you very much for your attention and patience.
Okay,